they have told that the rate of the reaction will be raised 5 times. And they have given the difference in temperature. When the catalyst which has been used in a chemical reaction, it forms a temporary bond with the reactant and exists in a temporary state. During the chemical reaction, either heat is absorbed nor heat will be developed. So during this process, it never affects on the free energy change. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. My dear students, in our last discussion, we were dealing with the unit called Chemical Kinetics. Under that, we have discussed about the temperature dependence on the rate of the reaction, and also we were discussing about the Arrhenius equation. And also we have talked about the activation energy and the qualitative aspects in increasing the rate of the reaction with the temperature. Today, let us move on to the next topic of this unit about the collision theory and the effect of catalyst. And also we are going to understand about the effective collision. Before that, let us discuss some of the numerical based upon the Arrhenius equation. So, what does the first numerical tell us? If the rate constant for a reaction is 1.6 into 10 to the power of minus 5 and 6.36 into 10 to the power of minus 3 per second at 600 Kelvin and 700 Kelvin respectively, calculate the energy of activation for the reaction. We need to calculate the energy of activation, and they have given the difference in temperature as well as the rate constant they have given, and also they have given the R value. Let us see how to calculate. We know that Arrhenius equation tells us that log K2 divided by K1 is equal to EA divided by 2.303 into R into T2 minus T1 divided by T1 and T2. This is a Arrhenius equation already we have learnt. Now they have given the temperature differences. The larger temperature is T2. So T2 we know that how much it is? 700 Kelvin and T1 is 600 Kelvin. Is it right? And they have given the R value 8.314 joules per Kelvin per mole, and also they have given the K2 and K1 value. What is K2 here? 6.36 into 10 to the power of minus 3, and K1 is nothing but 1.6 into 10 to the power of minus 5. Now you substitute this value to the Arrhenius equation, you will get log, what is K2 here? 6.36 into 10 to the power of minus 3. What is K1? 1.6 into 10 to the power of minus 5 is equal to, what is EA? We don't know because we need to calculate the energy of activation. So EA is equal to EA divided by 2.303. What is the R now? 8.314 into, what is the T2 now? 700 minus 600 divided by 600 into 700. Is it right? This is how we need to substitute the K as well as the R and the T value to the Arrhenius equation. Once you substitute this, now you do the division of 6.36 divided by 1.6. You will get 3.9, and if you take the logarithm for that, you will get 2.5993. 2.5993. This is a log of 3.9, and we know that EA divided by 2.303 into 8.314 into 100 divided by 600 into 700. Now, we know that we need to calculate the EA. I'll take out the EA outside. EA is equal to 2.5993. I'm multiplying these two into 2.303 into 8.314 into 600 into 700 divided by 100. Divided by 100. You can cancel with the double zero here and there, and if you do the multiplication for these, you will get EA is equal to 209.0 kilojoules per mole. This is how, we need to substitute the entire given data to the Arrhenius equation, and finally we obtain the EA value. This is the energy of activation. Hope you all understood with this calculation now. Now let us see with another numerical. The rate constant for the first order reaction becomes 5 times when the temperature is raised from 350 Kelvin to 400 Kelvin. Calculate the energy of activation for the reaction. Here, they have not given the K2 and K1 value, but they have told that the rate of the reaction will be raised 5 times, and they have given the difference in temperature. So, we know that rate constant of the first order reaction becomes 5 times then the temperature is raised from 350 to 400 Kelvin. Now, we know that T2 is nothing but a 400 Kelvin and T1 is a 350 Kelvin, and we know that what is the R, that is 8.314 joules per Kelvin per mole, and the K1 value we don't know, and the K2 is obtained by 5 into K1 because which is a 5 times greater than the K1. Is it right? Now I'll write the Arrhenius equation, that is log K2 divided by K1 is equal to EA divided by 2.303 into R into T2 minus T1 divided by T1 and T2. Is it right? Now we know that log K2 is nothing but a 5 into K1 divided by K1 is equal to EA divided by 2.303 into 8.314 into what is the T2 now? 400 minus 350 divided by 350 into 400. Now, the K1 and K1 will be get cancelled. Log 5 I have to find out. If you find out the log 5, you will get 0.6990 is equal to EA divided by, if you multiply 2.303 into 8.314, 19.147 into the difference is 50 divided by 350 into 400. Now we know that again we need to find out the energy of activation. I'll take out the EA outside. 0.6990 into 19.479 into 350 into 400 divided by 50. Divided by 50. Now if you multiply all this numerical divided by 50, if you do it, you will get EA value as 37.47 kilojoules per mole. 37.47 kilojoules per mole is the energy of activation of this reaction. This is how we need to calculate the energy of activation by using Arrhenius equation. So here they have not given the K2 value, but I have considered it is 5 times greater than the K1. That is why I have cancelled out the K1 and K1 and I have found out the log 5. Okay, and I have done the remaining numericals to get the values of EA. Hope you all understood with this numerical. Next we'll solve the another one. The first order rate constant for the decomposition of ethyl iodide by the reaction C2H5I give rise to C2H4 plus I. So this is a decomposition reaction. At 600 Kelvin is 1.60 into 10 power minus 5 per second. Its energy of activation is 209 kilojoules per mole. Calculate the rate constant of the reaction at 700 Kelvin. Again here they have given the T2, that is 700 Kelvin they have given, and the T1 is 600, and they have given energy of activation. What is that? 209 kilojoules per mole they have given. Along with this, you can see that they have given the K1 value, that is 1.60 into 10 power minus 5 per second. Now we need to calculate the K2. How to calculate the K2 now? Let's see. Now I'll substitute the values to the Arrhenius equation. Log K2 divided by K1, which is equal to EA divided by 2.303 into R into T2 minus T1 divided by T1 and T2. So what is the log K2 here? We don't know, but we know the K1 value. What is it? 1.60 into 10 power minus 5 is equal to, what is the EA? EA value is 209 divided by 2.303 into 8.314 into, what is the T2 now? 700 minus 600 divided by 600 into 700. This is the first step where I am substituting the values of K1, EA and T1 and T2. Now 209 divided by 19.147 into 100 divided by 600 into 700. If you solve all these things, you will get 2.5989. 2.5989 you will get, and we know that on this side we are getting K2 divided by 1.60 into 10 power minus 5. Now I'll take this log on this side. It will become an anti-log. So it can be written as K2 divided by 1.60 into 10 power minus 5 is equal to anti-log of 2.5989. We know that 2 is a characteristics. We need to find out the anti-log for 0.5989. Is it right? How to find out this? I have a log book. So here I have a 0.89, 0.59 I have. What is my value? I have considered 2 as a 0 because it is a characteristics. So 0.5989. So 0.598, this is a value under the 8, that is 3.63, and we have to see the 9 for this. Is it right? This is how we will find out the anti-log values. Now, after obtaining 3.963, you have to add the 8 for that. You will get 3.963 plus 8, you will get 3.971. 3.971 because I am taking 0.59 under AH and I have added the mean difference is 9 and you will get a 8. Is it right? So the answer is 3.971. After obtaining this anti-log value, I'll write it here so that you will understand. So K2 is equal to 3.971 into 10 power of 2 into 1.60 into 10 to the power of minus 5. Okay, why this 2 has come? Because this is a characteristics. I have taken this as a 0.5989 and after obtaining the antilog for this, we have to add this to raised to the power of 2. So that is why I have written 10 raised to the 2. So now you solve this numerical, you will get 635 into 10 to the power of minus 3 meter per second. This is the values of the K2. So first thing is, in this entire numericals, first they have given the K1 value, but they have not given the K2 value. That is why I have substituted like that. But they have given the EA along with R and T2 and T1 they have given. So after substituting this, first I have solved all this right hand side. You will get 2.5989. So after obtaining this, on the left hand side, we have log of K2 divided by 1.60 into 10 power of minus 5. So I'll take out this log outside, it will become an anti-log. For this, we need to find the anti-log for 0.5989. Why is it so? Because the 2 will become a characteristics. So it will become raised to the power of 2. Okay, that is why I have written 3.791 into 10 power of 2 into 1.60 into 10 power of minus 3 and finally you obtain this answer. This is how you know if they have given the K1 or if they have given the K2 or if they ask you to calculate the EA, that is energy of activation, we can easily calculate it by using the Arrhenius equation. Hope you all understood with all the 3 important numericals. Now let us understand what is the action of catalyst. That is the effect of catalyst. We always know that the catalyst which we are using in the chemistry, either it increases or decreases the rate of the reaction, or we can say that it always alters the rate of the reaction. Let's see how does it alters. The catalysts are the substances which alter the rate of the reaction without itself undergoing any permanent chemical change. Here I have a reaction where KClO3, which is undergoing the decomposition, you can say, in presence of manganese dioxide as a catalyst, it will form KCl plus 3O3. So in this reaction, you know, the MnO2, the manganese dioxide is a catalyst. It increases the rate of the reaction or it decreases the rate of the reaction, but it never undergo any permanent changes. Okay, but this nature of the catalyst can be understood by 2 theories. The first one is intermediate complex theory and another one is collision theory. First, I will explain what is an intermediate collision theory. According to this, a catalyst which participates in a chemical reaction by forming a temporary bonds with a reactant resulting in intermediate complex, and this is a transitory existence and decomposes to yield a product and catalyst. What does it mean? When the catalyst which has been used in a chemical reaction, it forms a temporary bond with the reactant and exists in a temporary state, that is unstable. During the decomposition, it converted into product. Let's see with the graph now. So here I have plotted the potential differences or the potential energy versus reaction coordinate. Here you can see that I have a reactant, okay, this is a reactant. So during the reaction, we know that reactant molecules will be collide with each other. During this collision, it will gain some energy that is said to be threshold energy or activation energy. So when they get the energy, you know, they will form a complex, that is an intermediate complex will be formed. So this is a threshold energy. Is it right? So this threshold energy, once it is gained by the collision of the molecules, it will form a intermediate complex. This intermediate complex is unstable. During the decomposition, it converted into product. It converted into what? Product. So during the steps, it will gain some energy that is known as activation energy. That is known as activation energy. You can see that the distance between this is the activation energy. Suppose if I add the catalyst to the reaction, we know that the catalyst will be react with the reactants. It will form a temporary bonds with the reactant and forms a intermediate complex at this point. At this state, once it forms an intermediate product, the energy of activation for this kind of reaction is very, very, very small as compared with the reactant alone. Hence, during this decomposition, it finally gives rise to the product. This shows that when you add the reactant along with the catalyst, their energy of activations will be suddenly gain up and it is very short and it can easily forms a product as compared with the reactant alone. So this is a theory was explained by intermediate catalyst or the intermediate complex formation. Next thing is effect of catalyst. Some of the important characteristics I have mentioned here. Let us see what are the important characteristics of the catalyst. A small amount of the catalyst can catalyze the large amount of reactants. A small amount of catalyst can catalyze the large amount of reactants. Is it right? The catalyst does not alter the free energy change, which means that during the chemical reaction, either heat is absorbed nor heat will be developed. So during this process, it never affects on the free energy change. That is, delta G of the reaction is not get altered. Similarly, the catalyst, it does not alter the enthalpy of that reaction. Okay, that is the delta H of the reaction is not altered. And the catalyst can catalyze the spontaneous reaction but not the non-spontaneous reaction. So this is very important because in the non-spontaneous reaction, the reaction cannot be proceed of itself. So for that, some amount of energy is required. Is it right? But in case of spontaneous reaction, the reactions will be taking place of its own, even with the help of catalyst also. Here, the catalyst will be mainly used only with the spontaneous reaction. Next thing is, the catalyst helps in attaining the equilibrium faster. That is, the catalyst can catalyze the forward as well as the backward reaction due to some extent so that equilibrium state remains same but not reached earlier. So when you add the catalyst to the reversible reaction, we know that in a reversible reaction, both the forward and the backward reactions which is happening. When you add the catalyst for this, the forward and the backward reactions which is taking place with the same time, we can say, with the same extent, we can say that. Okay. So once the forward and the backward reaction which is happening simultaneously or to the same extent, equilibrium will be exist. So that equilibrium will be maintained only when you add the catalyst to the reaction. So hope you all understood with all the 6 important characteristics of the catalyst when it is used in the reaction. Now, that is the last topic of this unit, that is collision theory of chemical reactions. According to this theory, the reactant molecules can assume to be hard spheres and the reaction is postulated to occur when the molecules are collide with each other. So what to be considered here? Here, the reactant molecules should be in a hard sphere and they must collide with each other. This is the condition for the collision theory. What is the condition for the collision theory? The collision molecules must be in the hard sphere and they must collide with each other. In this, we need to understand what is a collision frequency. What is the collision frequency? A number of collision per second per unit volume of the reaction mixture is said to be collision frequency. Imagine I am doing a reaction in the beaker. In this, there are certain different molecules. There are different molecules will be there in the reaction. Okay. At a particular second, I'll consider the unit volume of the molecules in this. At 1 second, in one volume of the molecule, the number of molecules will undergo collision, or you can say that at this volume, how many number of molecules undergo collision in 1 second, that can be calculated by using collision frequency. So, what is the collision frequency? It is the number of molecules get collide in 1 second in one unit volume. So, that is said to be a collision frequency and it is denoted by Z. So, here I have taken out the reaction where A plus B giving rise to product and the rate of the reaction can be expressed for this is rate is equal to ZAB into e to the power of minus EA by RT. Then what is the Z here? ZAB represents the collision frequency of the reactant A and B. What is the collision frequency here? Collision frequency is a number of molecules, number of reactant we can say. Number of reactant when they collide in a 1 second in one unit volume. Okay. Represents the fraction of molecules with the energy equal or greater than EA. By comparing with the Arrhenius equation, we can say that A is related to collision frequency. So, all the collision do not lead into the formation of product. It is very, very important. So, according to the Arrhenius, we already know that almost all the collision is not leading to the formation of product. Only when the molecules are collide with gaining some energy known as threshold energy by forming an activated complex, it will lead to the formation of product. Okay. So, that is why we need to understand effective collision. What does it mean? Effective collision are those collision which are lead to the formation of product, and the number of effective collisions are governed by two factors. One is the energy barrier and next one is orientation barrier. What is the energy barrier? The collisions are effective only when the molecules possess some energy greater than or equal to the threshold energy. So, what is the energy barrier? Here, if the effective collision has to be become effective, the collision molecule must possess the energy greater or equal to the threshold energy. And coming into the orientation barrier, the reactant molecule must collide with the favorite orientation in order to facilitate the breaking up of old bond and formation of new bond. So, during this collision, the molecules must favor the orientation of breaking and formation of bond. So, this orientation of barrier which tell us that how molecules will go for the formation of bond and the breaking up of bond. Here, I have an example for this with the methanol along with the bromoethane. So, you can see that methyl bromide which react with the nucleophile and forms a methanol and forms what? Methanol along with the bromine. So, in this we know that OH is a nucleophile which attacks to the beer and replaces the beer to form a methanol. Is it right? So how we know that in the methyl bromide, the bromine will get the negative charge, whereas the carbon will get the partial positive charge. When a nucleophile comes and attacks to this position, we know that the bromine is also having the partial negative charge and our nucleophile is also having the partial negative charge. So that repulsion will be taking place. Then in which position this OH minus ions has to be attacked? From this direction, which is opposite to that of the bromine. So this nucleophile has to be come and attached to the carbon in the opposite directions of that bromine. Then only the proper orientations will be taking place in the molecule and lead to the formation of product. But if the nucleophile as well as the bromine, if it is there at a single site, the repulsions will be caused. Why is it so? Already I explained that the bromine is also having the negative charge. OH is also having the negative charge. Negative charge will be repulsed with each other. So that there will be no formation of bond. Only when the opposite charges are attracts, which lead into the formation of bond and leads to the formation of intermediate complex, and this intermediate complex will be decomposed to give a product. This is how the orientations of the nucleophile, it also very important when we are talking about the collision effect or the effective collision. So the proper orientation of the reactant molecule leads to the bond formation, whereas the improper orientation which does not make the molecules to undergo product. In such situation, to account for the effective collision, another factor called as P, known as probability or steric factor. What does the P represent? Probability factor or the steric factors which has been introduced. So that the equation rate will be become rate is equal to P into ZAB into e to the power of minus EA by RT, where P is a probability factor and ZAB is nothing but a collision frequency of the reactant, that is A and B respectively. Thus, the collision theory, activation energy and the proper orientation of the molecule together will determine the criteria for the effective collision. Hence, the rate of the chemical reactions will occur. So, what is important to occur the rate of the reaction? So, activation energy and the proper orientation. So, here P represents the probability of steric factor. Is it right? Proper orientations and activation energy as well as the collision in the molecule are very important to occur a chemical reaction. So, hope you have understood with this collision theory and how does the catalyst, which play a very important role in the reaction, also have explained that. So, by this I like to say that whatever I have done in this session, especially the numericals as well as with the catalyst nature and the collision theory, have a look on it, and wherever you are not understanding the numerical, pause the video and write once again and practice well, because in this unit we can expect 1 numericals from this unit. Hope you understood. We'll meet you in the next session. Till that, take care and be safe. Thank you.